Welcome again to the PLC Professor's Workshop. In this lecture discussion, this is a lab project lecture discussion, M27, and it revolves around the virtual machine. If you have not already watched that lecture, you need to go back and watch that one, the virtual machine, because that's the machine that we wrote this program for. And there are three categories that we're going to look at. The first one is using latch and unlatch, or set reset. That's the simplest way to program. It's very quick and easy to do, but it's not so easy to troubleshoot, and it has its limitations. Well, first we're going to do just set. We're going to set all of these sequence bits as we go through the sequence, and then reset them all at the end. In the next discussion, we will do set and reset. In other words, we will set the bits, and then in later steps, we will reset earlier steps to free them up to allow another part to come into the machine. Then the final will be seal in logic, where we use no latches or sets, therefore no unlatches or resets, which is the most challenging form of programming, but it's the easiest to troubleshoot, and it's the cleanest in operation. So let's jump in there and take a look at straight up set logic. This is the logic as we left it in the manual. I've narrowed up the screen for the logic so I can have room for the simulator. Now, I originally did these lab projects with actual hardware. I did them with an LC20, some with LC50, and some with LC70. But we're going to do them with the simulator just to demonstrate, frankly, using the simulator, because I realize most of you probably aren't purchasing hardware. Something that I'm going to do real quick here that we've covered in a former lecture, and that is I'm going to do a Control-Alt-Delete. I'm going to go to Task Manager, and I'm going to right-click on CCW Shell, and I'm going to say Set Affinity. Which processes are allowed to run this particular app? I've got just 3 CPUs selected. So when this comes up, it probably looks like this. So I unselect all processors because I think I have 12. Yep, 0 through 11. And then I select just the first couple. The reason for doing this is that Rockwell says that the computer's running too fast, and it actually is trying to do things before it's ready, and then it does a watchdog timeout fault. So if you're getting those, then you need to go in and do this. Now, if you do this for CCW Shell before you open the simulator, then the simulator falls under this configuration. Otherwise, if you've already started your simulator, you have to do the same thing with the simulator. And I will show you that. Go back to Processes. You see there's the Connected Components workbench, and there's the simulator. Right-click on that, go to Details, and then down here, see Micro 800 SEM EXE. Right-click, Set Affinity. See, it's set, just like CCW is. So if you do this for CCW right off the bat before you open the simulator, you're covered. Otherwise, you got to do both. Okay. Now, will this ever disappear from the landscape for using the simulator? I have a suspicion that it won't, simply because it's kind of a loose end that allows anybody's operating system and computer and setup to run the simulator. In other words, if they tighten it up too tight, then it might not work correctly in all cases. So even if we all had Windows 10, that doesn't mean we have the same version. That doesn't mean that we're running 32-bit, 64-bit. There's just too many variations for them to account for. So I think that's going to stay that way at least for a while. Okay, so let's look at our logic. And you notice right now that there are 5 outputs on. If you look over here at the simulator, you'll see output 5, 11, 12, 13, and 14. So let's go down through here and look at what those are. Output 11, as you can see here, output 11 and 12 are on. If we scroll down, there you see output 14. And if we keep looking, there's 13 right there. Now, output 5 is, I'm going to have to look for that. I don't remember what it is, but it's in here somewhere. Okay, that's input 5. And output 5 right there. extend cylinder 5 solenoid. And that's a cylinder that we don't use very much. It's all the way at the end of the process, and we could actually live without it. It's a stop that extends out onto the finished product conveyor to prevent any product from going on out of the cell downstream. And primarily it's there at the behest of the downstream station that wants some control over whether or not product can come down that conveyor. So this prevents it entirely. So going back to the top, now remember in this logic we are doing set and reset. We're not setting and resetting the steps. So notice that S1, S2, the steps themselves are not being reset until you get all the way to the end of the program right here. And this is where we reset all the steps when the part is leaving this station. So step 7, finished part leaving. When that happens, we're going to move a 0 into the part number, and we're also going to reset all the steps. Now the reason that we have set and reset for the outputs is because they are solenoid valves. So there's a valve to retract and a valve to extend, or rather I should say there's a solenoid. They're double solenoid valves. So one solenoid shifts the spool in one direction and causes the cylinder to extend, and then if you turn that off, it's spring return to center. It holds position. If you energize the other solenoid, then it causes the cylinder to go to the opposite position. So that means you have an output to extend and an output to retract. Now we didn't have to do it that way. We could have used single solenoid, spring return. You energize the solenoid, it extends. You de-energize it, it retracts. So the spool in the valve itself is spring loaded, and it only has 2 positions. What we're using is a 3-position valve with 2 solenoids. So that's why we have to turn off the retract before we can turn on the extend. It makes for a little bit more clutter in your code. There's other ways of going about it, but we're really not worried about that variation of situation right now between single solenoid, double solenoid, spring return to center, detent, etc. Because you could use double solenoid valves that are detent, meaning if you energize one solenoid, it extends. You de-energize the solenoid and it stays right where it's at with the cylinder extended. And then when you energize the other solenoid, it pulls the spool over to that end and retracts the cylinder. You turn off that solenoid, but it stays retracted. In other words, it's detented. Okay, so looking at this logic, it's pretty simple. Remember, we're kind of simulating everything. So over here in our programs, we're buffering inputs, we're buffering outputs. That's not necessary for this particular application, but it's a good habit to get into. And just to revisit that real quick, you see I'm taking the embedded I/O embedded digital input 0, and whatever that is, I'm transferring that state over to this tag or memory location or pointer or variable, whatever you want to call it, IN00. And then it's alias to photo I1 new part. I would rather program with IN00 than with _IO_ embedded _ digital input _00. This is a mouthful here. Once you got used to it, I guess you could type it in easy enough. I like input 0. So for this particular application, I'm buffering it for no other reason, so I can use these tags, these variables, instead of these over here. So when we write our program, then we write to not to actual I/O. This is not output 11. You see output 11 is on over here. That's not output 11. If we go down to our buffered outputs, you can see, and I'll scroll down here, see output 11, OUT 11, retract cylinder 1 solenoid. That's what I'm writing the execution to, but in the buffered outputs file, that value is being copied over to the actual real embedded output. Okay, so enough for that. Back to sequence. And in our very first rung, if you turn on input 0, that's photo I1. And remember, we don't have real photo eyes. We're using the mouse to toggle on input 0. So if I toggle on input 0, okay, it's going to scan the barcode on the part. And if the part number is greater than 5,000, which you can see it is here, then I'm going to set a part in queue. Now, if I don't do anything further, technically this part has gone through photo I1 and now it's going to pass through photo I2, and if I don't react, it's going to go right on through and out of the system. So we turn off input 0 and we turn on input 1. As long as we do that in a reasonable length of time, we're kind of simulating, when we turn on input 0, the part didn't stop moving. It's still moving through the barcode scanner. And so eventually it's going to get down to the entrance of this work cell, and we need to energize cylinders 1 and 2. One is the stop and the other pushes it off of the conveyor and into the workspace. So right now we've extended it into the workspace. In the meantime, this thing has gone on with the sequence. So the sequence has been running all this time that we've been talking. If I scroll down here to see where it stopped, I can see that S6 completed, cylinder 3 extended. Now, if you remember your virtual machine, that means that the part is pushed out onto the finished product conveyor. But the finished product conveyor is not running yet. It can't run until cylinder 3 retracted proc sees this cylinder piston, which it has. This is true. And input 4 is not on, meaning there is no part at the last stop on the finished product conveyor. However, we haven't turned on input 3 with our mouse, which says that there is a part at the end of stroke for cylinder 3. So I'm going to go turn on input 3 here. And when I do that, the finished product conveyor is going to run. So now picture in your mind that part is now moving towards the last photo eye, which is input 4. So I'm going to turn off 3, because once the conveyor pulls that part, it pulls it out of that photo eye 4, which is input 3. And eventually it will get to the next photo eye 5, and turn on that photo eye. And when it does, the conveyor stops. And the reason the conveyor stops, if you look up here, is because we have no downstream call. Because there is no downstream call from the next cell downstream, then we have extended cylinder 5. So cylinder 5 is out there blocking the way. So that part's not going anywhere anyway, even if the finished product conveyor was running. Let's go ahead and get rid of this part. Okay, picture in your mind, it's setting in front of the stop controlled by cylinder 5. The conveyor's not running. So let's say that there is a downstream call. So we'll turn on input 5. Go back up here a little bit. We're going to turn on input 5. And when we do that, the conveyor, watch here, is going to start running. Okay? It starts running, and the part is still in front of that sensor that's input 4 right here, photo eye 5. It's still there, but the conveyor is pulling it out of that photo eye. So let's turn off input 4, and you see that the conveyor keeps running. That's because we need that conveyor to run that part all the way out of the system. But we don't want to leave that conveyor running forever. So we have a timer, 10 seconds, and if there's no part activity, in other words, step 1 isn't set, step 4 isn't set, step 6 isn't set, and there is nothing in front of photo eye 5. If all 4 of those conditions stay true, in other words, not, then there's no part activity. Now these 4 instructions could be right here in front of this on delay timer that you see in 16. The reason I broke it up this way is to try to keep the program on the screen narrow, meaning less width. I think I could probably squeeze that all in there, but this puppy right here, this TON, it takes a lot of space. So if we move that up to here, chances are this rung would be wider and we could keep this screen this narrow. Okay, no part activity. Now, if I go in and interrupt this, okay, so picture this. The system is empty, right? This step 7, finished part leaving, that happened, and when it did, it reset all of the cylinders, all the solenoids, and it also, besides moving a 0 into the part number, it also reset all the steps. So this thing is sitting here in kind of a state of waiting. So theoretically, I'm going to leave that downstream call on, and I'm going to bring another part into photo I1 up there at the beginning. So we should have a new part queued. Now it reaches photo I2 and it gets pushed off. You can see the outputs changing down here. And eventually that's going to end up here waiting for input 3 on. Okay, so when you see here, Solenoid 3 retracted procs, we can turn on input 3 now. So it's going to turn on the finished product conveyor. We can turn off because it pulled it out of that photo I. Now it reaches 4. And because there's a downstream call, the conveyor is still running. So it goes right back off. It passes right through. Now we're into the 10 seconds of no part activity. And when that times out, voila, the finished product conveyor shuts off. So as parts come in, if they stop at input 4, photo I5, it'll be because there's no downstream call. If there's a downstream call, that would have retracted cylinder 5 right here. Here's cylinder 5. See? If there's a downstream call, then you reset the extend and set the retract solenoid. So this code is real simple. Now I tried to mix it up a little bit here. I'm using a pulse rising true if on instruction to reset part present solenoid 3 extended, and I'm using when the pulse goes off to say that the part is left. So in other words, when this is part present solenoid 3 extended. So that means there's a part sitting in front of the extended position for cylinder 3 on the finished product conveyor. If the part arrives at photo I5, that meant it left the other photo I, so we can turn that off. When it arrives at photo I5, input 4, then we can say when it arrives, that's what this is, positive pulse. In other words, the leading edge. When it arrives at photo I5, it's no longer at cylinder 3 extended position. When it leaves input 4, photo I5, that means the stop's not extended and the conveyor's pulling the part away from photo I5. Therefore, the finished part is leaving. That's probably the only complex code in this logic, is these two instructions if you're not familiar with one. And what we did with other platforms is we would use a true if on, then a one shot. True if off, then a one shot. Therefore, the rung would be true when this instruction went true for one program scan. In the case of a true if off here with a one shot instruction, then this rung would be true when the rung went false for one program scan. Same thing. Actually, this is pretty cool. We'll call it positive or leading edge of the pulse and the trailing or negative edge of the pulse. Okay, so that's our code for set. But notice that we're not resetting the steps until all the steps are complete right here. S7, finish part leaving, then that clears all of these steps, including itself. It also turns itself off, and then this is ready for another part. So with this code, very easy to write, very easy to follow. The challenge is that you have to reset all of these steps, and you can't put another part in here until the part is all the way out. In other words, back up here in the beginning, you can't do any of the early stuff. You know, part can be in queue, but you cannot run this logic again because you haven't reset step 1. So in other words, step 1 is already set from the last part that went through. So the next thing we're going to do is we're going to talk about logic where once you're done with a step, you're going to reset it to clear the way for another part to come in behind this one. so you can end up with more than one part in this station at a time.